This is the Sealant and Waterproofing Association of Canada. We have slightly switched gears. There's a long-term vision to help grow the association and reach beyond our current borders, our former borders of Ontario. And we do have some people that are logging in from Alberta. And we also have some people logging in from the furthest, most western province of British Columbia. So welcome. I can't hear them, but thank you. So introducing the seminar, we are talking deep energy retrofits. The subject and description as provided by our beautiful guest speakers over here. Buildings are the foundations of our communities, but their emissions are contributing to a climate crisis that threatens to destabilize this foundation. Collectively, we must work to design, construct, and retrofit buildings for a low-carbon future. In our work with developers, contractors, architects, and local government, we will help tackle these challenges of achieving net zero today and to meet the surging demand for decarbonization across all sectors. This presentation will help frame the conversation for our SWA stakeholders, discuss building envelope design, deep energy retrofits, case studies, and focus on solutions for improving the overall building performance. The presentation will also focus on how sealants and waterproofing are a key to meeting this challenge of net zero. So our two speakers, both are from WSP. Welcome. We have Jason Paulos. He's a project manager with WSP, where he specializes in building science, new development, restoration of existing buildings for a diverse portfolio of properties in Ontario.
SWA for having us and hosting us. My name is Christian Flores, and today we'll be talking about high-performance building envelope design, deep energy retrofits, and how sealants and waterproofing are key to improving the building performance. So our agenda for today will be setting the stage and talking about the bigger carbon picture and what our current climate goals are. Second, we'll be talking about initiators for change. We'll look at how these goals are being addressed at the policy and regulatory level. Third, we'll talk about charting a path to net zero and what types of projects are necessary at the building level. Number 4, we will talk about retrofits, deep energy retrofits in a bit more detail. We'll cover a few case studies and finish with a call to action on how we can help our clients plan for more holistic retrofit projects. At the end, we'll have hopefully some time for some Q&A. We have a lot to cover and only 1 hour to do it, so let's get on with it. So the bigger carbon picture. Before we start talking about retrofits, we need to talk about the context of why we're here and why this matters. This is the latest temperature projections from the 2021 climate report by IPCC. The different curves show how much the temperature is projected to increase for the remainder of the century based on a certain amount of carbon emissions associated with each scenario. So the top curve being sort of the worst case scenario, if emissions keep increasing year over year, this is sort of the temperature that we're expecting at the end of the century. I want to highlight a couple of findings from this report. First, we are currently en route for a 1.5 degree increase by in the next couple of decades. So now the policy goal is to try to maintain the temperature increase below 2 degrees by the end of the century. And that's represented by this curve here. This curve also assumes that we get to net zero by 2050. So when you hear the phrase net zero by 2050, now you know where it's coming from. So those are global average temperatures. Canada happens to be the country that will experience the most amount of temperature increase in the world. We've already seen a 1.7 degree increase since 1950. And as you get further north, the temperature increase will be even more severe. So what that means for our buildings is the risks for extreme weather events are increasing. In Calgary, they refer to it as climate change hazards, and it includes more intense storms, risks for flooding, and also more extended heat waves and higher temperatures. In Saskatchewan, the same. We're expecting drier climates and more variability in the climate. This is happening all over the country. In Toronto, it's a similar story. The number of days where the temperature will increase will be above 30 degrees. It's expected to triple by the 2040s. We're expected to have longer and more frequent heat waves and more intense storms. So what can we do about it? It's not all just doom and gloom. There's a big opportunity for us to really change the course. For us working in the building industry, we have a big opportunity here because over a quarter of the carbon emissions in Canada come from buildings. In the GTA, the buildings are actually the largest source of carbon emissions because of the energy it takes to operate them and the carbon involved in the construction of them. So now let's talk about how our building codes and legislation are trying to address the issue. So for new developments, it's fairly straightforward, right? Energy codes are becoming more and more stringent, demanding buildings that are more airtight, better insulated, and with mechanical systems that are powered by electricity instead of burning fossil fuels. As you know, in Toronto, we have the Toronto Green Standard that has different tiers that require better energy efficiency as you go from tier 1 to tier 4. And the goal is that by 2030, we are building buildings that are net zero ready. But the problem is we can't just focus on new construction because most of the buildings that will be around in 2050 have already been built. And many of them without any energy requirements at all. So that means that even starting today, even if every new development is built to net zero standards, we still won't be able to reach our carbon reduction goals. We really need to focus on improving our existing building stock. And I really like this graphic on the right side here because it shows clearly the relatively small impact that new buildings will have on the overall carbon emissions, right? It shows the date of construction for residential buildings in Canada, and it's projected to the year 2030. But you can see in the area in blue at the top, that's the new buildings that will be constructed or that are projected to be constructed. So if we're only worried about energy codes, we're really just reaching the tip of the iceberg. No pun intended. So the federal government has recognized this and has committed to some key measures. Setting a price on carbon that will increase over time. Updating the National Energy Code to net zero standards to be in place by 2030. And creating an existing building model code that will include emission targets. And I'll get back to this in a minute. But the government realizes that this will require a massive amount of investment into our buildings. And so they've developed different funding opportunities for these deep energy retrofit projects. In Toronto last year, the city committed to energy policies for existing buildings as well, requiring energy reporting and benchmarking our current building stock, requiring audits and recommissioning of our existing mechanical systems, and also establishing mandatory emission targets by 2025 for existing buildings. So this is coming, and we need to start thinking about how we will retrofit all these existing buildings that are very inefficient. This is in line with other municipalities across North America. In 2019, New York City passed Local Law 97 to start limiting carbon emissions from existing buildings. And in Vancouver, WSP has been helping the municipal government to determine limits on greenhouse gas emissions for existing buildings that will be implemented in 2030. This, of course, will create a massive retrofit market and a great opportunity for anyone looking to improve the efficiency of our existing buildings. So we have seen why changes are needed and what is being done at the policy and building code level. Now let's look at what actually needs to be done at the building level and what kind of projects we can look forward to. So there have been multiple studies and reports done on this topic. They mainly boil down to these four main categories. One, recommissioning and optimizing our existing building systems for improved control and performance. Two, deep energy retrofits focused on energy reduction. Three, incorporating solar or other on-site renewable sources. And four, switching to low carbon fuel sources. But remember, it's not just about reducing energy consumption. Two buildings that use the same amount of energy may have drastically different carbon emissions at the end of the day. And this is because the carbon emissions will vary depending on how the electricity is generated. So if you have a building that's serviced by an energy grid where the electricity is produced by burning fossil fuels, obviously that will have a much higher carbon emissions at the end of the day. So when we talk about low carbon design, we need to consider more than just the carbon required to operate the building, what's called operational carbon. We also need to consider the carbon that it took for the building to be constructed in the first place, what's called embodied carbon. So that's why maintaining or retrofitting an existing building, even though it may not be the most energy efficient building, is much better from a carbon perspective compared to knocking it down and building a net zero building, for example. And this is where those of you who are manufacturers or work for manufacturers will be directly involved by the use of EPDs, environmental product declarations. So EPDs are like the nutritional facts that you find on any food product. It tells you the environmental impact that a certain product or material will have from a life cycle perspective. And if your company has not done these before, just be aware that the requirements are coming. At first, there won't be specific product requirements in terms of EPDs, only requirements for disclosure of the environmental impact. Programs like LEED version 4 already provide LEED points for EPDs. We expect that eventually legislation will start requiring EPDs on new construction, which will promote products with lower environmental impacts. We also need to take into account embodied carbon in retrofit projects. So this graph shows the sum of embodied carbon and operational carbon over the life of a building. And it starts above zero because of the embodied carbon, related to construction. And it increases from there due to the operational carbon, related to the operation of the building. So when we look at a retrofit project, if it is, you can see the carbon line basically jumps up immediately because of the embodied carbon related with that project. And if it's a like-for-like retrofit, as in the performance is not increasing from this retrofit project, it will continue in the same trajectory as previously. But if we start considering more energy efficient retrofits, we can actually regain a lot of those carbon emissions that were expected to continue. And this is the idea of reinvesting embodied carbon and having returns in terms of carbon savings down the line. And going further, if we start looking at deep energy retrofits that include, on-site renewable sources, we can perhaps provide electricity back to the grid, and in the end, at the end of the life cycle of the building, you might have negative carbon emissions. So looking at the life cycle of the building, we can try to identify when these retrofit projects are supposed to occur. Because typically as problems arise, building owners will be restoring or renewing their enclosure facade components in response to complaints from the occupants, leaks, cracks, or any other safety issues. But we need to be stepping back and looking at the bigger picture. What is a more efficient and effective way to maintain your building enclosure while meeting the overall needs of the building, including those for energy performance? Let's consider our existing building stock. The reality is that the majority of our buildings are rapidly aging. This map of the city of Toronto shows that the majority of the downtown core was actually built between 1961 and 2003. According to Natural Resources Canada, over a third of commercial and institutional buildings were also built in the 70s and 80s. So today, most of these buildings are between 30 and 50 years old or older. Now, buildings can sort of limp along with old HVAC systems for a long time. And similarly, IGUs can last for a long time as well. And sealants, well, they're typically considered maintenance if you're not doing a proper sealant replacement job, right? But a lot of these buildings have already had a holistic retrofit opportunity and that we've missed. The next best window, it's a little cut off there, but it's actually today. Within the next 5 to 10 years, most of the building owners that own these buildings should consider holistic approaches to renew their building systems in an efficient and effective way as these building systems start to age and terminate their service life. So going back to how these buildings will be decarbonized and approach net zero, the key priorities are to reduce loads by having high performance enclosures, improving the energy efficiency of M&E systems, fuel switching and strategic use of renewables is also important, but every building is different. There are many ways that we can reach net zero, and some will focus more on enclosure retrofits, others will focus more on the retrofit of mechanical systems and fuel switching. It will all depend on where the building is is in its life cycle, the types of mechanical systems used, and how the enclosure can be retrofitted. So the building enclosure controls in large part the energy loads of the building. It directly affects the indoor environment and the comfort of the building occupants. And it is critical for the resilience of our buildings to be able to adapt to the changing environmental loads from climate change. Because of this, we recommend starting with the building enclosure when owners start considering deep energy retrofits. So let's look at retrofits in a bit more detail now. I want to just quickly go through some building envelope fundamentals just so that we're on the same page, because these will be critical to understanding the energy conservation measures that Jason will be speaking about. So what is the building enclosure? It's the environmental separator for the building. It delineates what the indoor environment and what the outdoor environment is. And for this reason, it needs to control for the environmental loads imposed on the building from wind, precipitation, temperature differences, solar radiation, and so on. And it does this through four main control functions. The building enclosure includes thermal insulation, air barriers, water-resistant barriers, and vapor retarders. And all these have some impact on the energy performance of our buildings. But when we talk about reducing energy losses, we tend to focus on continuous insulation, reducing thermal bridging, having higher performance windows, window glazing that can protect against solar radiation or benefit from free solar heating, and airtight enclosures as well. So I will pass it off now to Jason, who will speak in more detail about building enclosure retrofits.
I'll just hold the mic. All right, thanks, Christian. So the next following slides, I'm going to explore some energy conservation measures, ECM for short, some of the things that we're going to be designing and specing, some of the things that you're going to be seeing moving on in the near future. So some examples that I'm going to be providing to you today is it's a snapshot of different building examples from different building typologies, heights, occupancies, and so forth. I tried to get a little taste of everything across the country. Of course, every region does have its own specificity with its own climate design. So just want to hope to share some ideas of what you guys can expect and the opportunities that can be seen from an energy and carbon perspective. So just a summary of what we talked about: walls, roofs, and windows. First one here is a ECM for overcladding existing walls. And this is, the most straightforward envelope retrofit strategy is simply by recladding it with additional materials to make the building have a better performance. And this can be achieved by a variety of different ways, different materials, different systems, with many different colors, architectural profiles, and so forth. And in this image below that I'm showing here is a reclad of an existing brick and masonry building, typical of the 1960s construction, that was reclad with a metal panel system, which could have been done with multiple types of systems such as EIFS and so forth. And what we did here was that you can see some of the details on the side here. A peerless thick membrane was applied to the existing structure. 4 inches of semi-rigid insulation was applied on the exterior, and then it was finished off with the metal panel. And by doing this, there's a lot of benefits of doing it overclad from the outside. Looking at the details here, we are protecting a lot of the existing penetrations, so that's improving the water resistance of the overall assembly. We're also addressing a lot of thermal bridging as well. You can see some of the details here. The one in the top right corner, the window perimeter is in contact with the steel lintel. So by overcladding, we are addressing a lot of the thermal bridging, slab penetrations, insulations covering that now. And the building that could have been insulated, this existing building was not, but if it was insulated with insulation within the cavity, these thermal bridging effects would have degraded the entire system between 40 to 70%. And you don't get this with an overclad system. So this is a tremendous benefit of doing that because we're addressing a lot of these past deficiencies in these projects and these sources of energy loss. And if you're coming to the reality of the new code changes in the NECP 2017 or 2020, thermal bridging analysis is now a requirement. So it's going to be a lot more focus on this for new buildings, and it's going to translate to existing buildings in the near future. Keep messing this up, sorry. So here's another example of, instead of an overclad, let's just replace the entire cladding system. So this is for a tall residential building, a few stories high, where we decided to completely replace the cladding with new. Again, we're putting the peel stick membrane, putting in a few inches of insulation, semi-rigid, supported by Z-girds, and then finished off with the metal cladding system. And in these applications, you can also consider doing an interior retrofit as well. And that means insulating from the inside. There are obviously challenges with that from a condensation perspective, but you can consider doing that if the building is trying to maintain existing appearance, such as a heritage building, or if you have constraints on site, such as tight setbacks with a lot of towers we have downtown. But there are benefits to doing overcladding as well, right? We're minimizing the disruptions to the building occupants, so construction can happen while these people are still living in the building. We are addressing the thermal bridging, and we're increasing the performance from a water management perspective and also heat loss perspective. And again, by overcladding as well, we are saving the existing materials. And to Christian's point as well, from an embodied carbon perspective, we have already invested in these materials that we're putting into the building. So by keeping it there, using it as a structure, we're using less material, less carbon, which is better for the planet. Next ECM I have here is for roofs, and this is simply adding in more insulation just to beef up the R value of roofs. And this can be tied in with any roofing project that's being done. When the membrane is no longer in good service and the roof needs to be replaced, there's an opportunity for putting in more insulation onto the roof, which can address thermal bridging, especially with older roofs that only have one layer of insulation. The joist between the insulation board is a big source for thermal bridging. We can also address thermal bridging at the parapets, where a lot of old buildings, the insulation does not wrap around. So by increasing the levels of insulation on the roof and also putting some insulation around the parapets, tying up the wall assembly, we're decreasing the amount of thermal bridging at the actual building. But there are challenges to doing this. It's not simply just putting in insulation. There's things that we need to consider as well, because as we're putting in more insulation, we're going to be modifying any solar panels that are on the roof, HVAC equipment which is set on the roof. Your parapet heights are most likely going to change, and especially these ones, when they're quite short, they might have to be rebuilt. And if you have any stairs or terrace doors that's exiting, it may not be feasible, or this design may have to change to accommodate that insulation. When it comes to windows, there's a variety of measures that we can do. Simple ones such as applying used sealant or weather stripping, just to keep the window airtight. Mid-range solutions could include replacing the entire IGU with something more higher performing. Something with an Argon fill, solar heat gate coefficient that's pretty low, lower emissivity coatings, and also spacers, high performance spacers to kind of bump up the R value of the window. For commercial buildings, it's a little bit more trickier because they usually use aluminum frames, which are poor performing, but there are opportunities of increasing the system R value by changing out the aluminum pressure plates with fiberglass, for example, is one way to significantly improve the performance of the window. There are much larger interventions as well. If budget permits, perhaps you may consider completely replacing the frames with something more bright performing. So if your building has aluminum frames, which are terrible for performance, you may consider doing something such as fiberglass frames, or aluminum frames with a thermal break to kind of help with the performance. This also gives you opportunity as well to kind of position the window that it aligns with the wall insulation, and this will help mitigate thermal bridging by doing so when you're doing these large scale interventions. Now, if you're combining this ECM with a potential overclad project, there's an opportunity to potentially decrease your size of window, and the reason you want to do that is because windows are not that great performing. So by decreasing the amount of vision area and increasing with more opaque, you're also increasing the overall building R value, retaining a lot more heat. This is also an opportunity to reduce the framing elements within the window itself, just showed you an example here of several operables in one punch opening. This happens in a few buildings. So we have the opportunity to reduce the amount of framing elements so that we're also improving the performance of the window. When it comes to below grade, this is similar to overpads as well. Adding in more insulation to the foundation walls, even if it's a building that's on grade, there's tremendous amount of benefits to putting in insulation, especially if you're doing a waterproofing project. This is the perfect opportunity to address the amount of insulation. If you're already excavating and you've already sealed all the cracks and applied the waterproofing, why not just put extra layers of insulation as well? A lot of buildings are uninsulated, so this is the preferred opportunity to do so when you're doing this type of intervention. So the last ECM that I want to present to you is a pretty simple one, and it's air sealing. And it's not as similar as the other ones. The past ECMs were dealing more about beefing up the insulation and retaining as much heat and energy within the building as much as possible. Air sealing is a different beast. It's quite common sense. Air transports a lot of energy. In your home, for example, 1/3 of your heat loss is mostly attributed to air leakage if you live in an old home like mine in Toronto. So by addressing, starting off with large penetrations, your mechanical systems have been abandoned. I've been on numerous sites where we have so many curves and openings that are just literally there, capped in sheet flashing, not really sealed. This is a perfect opportunity to, as part of your reworking work as well, to seal off these openings. It's the greatest source of air leakage. And once those are addressed, moving on to the smaller openings. I'm showing an example here. Pretty common, this is a precast building. It's a big box Home Depot type store where the sealant is the primary barrier between the joists of the precast. And having this type of breach here is introducing a lot of energy movement between the inside and the outside of the building. So, getting into some of the detailing here and tying into the ECMs, the ECMs can only work if it's constructed well, and this resorts to the SWA, the contractors we have here on site. Quality control is a huge thing when it comes to implementing these ECMs. It's, in many cases, when we are designing these energy conservation measures, we are not using traditional detailing. So we need to think outside the box on how we execute these types of work and have an understanding of the types of designs and details and materials that are going into place. So I put here in facade systems, we have so many different details, like thermal breaks and how it connects to one system and how the memory ties in and how the seal is terminating and so forth. And it makes a huge difference from an overall perspective from thermal, but also water as well. So the fundamentals is, as a collective, understanding the limitations of the materials that we're using on site in terms of compatibility, the weather applications such as weather, cold weather, self-sealing and long-term durability. And I put here, pre-construction meetings are essential. Introducing your team to the reality of the details and some of the targets that we're trying to meet in terms of air tightness as well. At the start of construction has a huge impact because this gives you the opportunity to clarify questions on the air barrier assembly. How does it tie in? What materials am I using? How does it cure? What is it compatible with? Organizing trade meetings so we have trained personnel on site to clarify how is this material installed, how the air barrier products being used, what membranes, tapes, and sealants are being used, and what is, and the most important, what is the sequencing of these materials? Because I've been on a site actually yesterday where the precast panel was installed before the sheeting or the peel and stick membrane was installed. So understanding that sequencing is huge in order to achieve these details, and if it's not built right, these ECMs that we design are not going to perform. These buildings are going to still emit large amounts of carbon emissions. Last point I have here is consider weather limitations of air barrier materials. Weather is a governing factor for most of our construction materials, and moisture and cold temperatures will affect adhesion, cure times, and even lead to damage if it's not properly installed. So whenever possible, air barrier products and substrate should be protected from cold weather. This is particularly a concern for products that also act as a vapor retarder, because you could be trapping in moisture if it's not constructed properly, and that moisture is just going to sit in the wall and deteriorate the wall assembly. And you know, a lot of manufacturers that are here have a lot of literature and sales reps that often provide instructions and test results just to show how these materials perform in cold weather. So there's an abundance of resources when it comes to using these types of waterproofing products. Common deficiencies that we see on site. This is something I deal with on a daily basis. Seals and penetrations do not exist or fully apply. Membrane is wrinkled or tented, so this gives an opportunity for water to penetrate the system and also air leakage as well. And transitions between different types of building assemblies is always a big one here, especially when it comes to roofs to walls or walls to below grade assemblies. Often the transition might be missing. There could be incompatible materials in contact with one another, which is a huge no-no. These materials are not designed to be together. The system will deteriorate or it may not even adhere to the surface. And also along window perimeters, I've seen multiple times reverse shingling, allowing water to kind of get in behind, or it's not sequenced in a way where water can shed properly. So one way of minimizing these efficiencies on site is really constructing mock-ups, and this is the primary opportunity for not only consultants and owners, but also contractors to confirm that the performance of the wall that's being constructed or any other assembly is adequate. Design intent has been satisfied, and this gives an opportunity for contractors as well to identify potential problems within the system from a constructability or coordination issue, and it might require multiple iterations to get this done right. And it's better to figure this out at the beginning of the project rather than at the end when we're doing a final walkthrough, because a lot of these issues that are not resolved at this stage could be full scale, and that can result in thousands of dollars, if not redoing a lot of the work that's on site. If possible, the mock-up should be constructed to allow for qualitative testing, such as water or air testing, that help identify any breaches in the membrane. And they should also include interfaces, challenging interfaces and components to verify the sequencing, the installation, and the methods that are critical to the function of the air barrier and water barrier. So some of that testing that we could do at the mock-up stage or even at the end of the project, I've listed some here. So right now the code is quite gray in terms of what the requirements are for existing buildings, but for new buildings, the NCP has introduced open whole building air tightness testing. So at the end of the project, you'd be using a door blower fan to pressurize the whole building just to see how big the building is. But in terms of small scale testing that we do to make sure that localized efficiencies are addressed or does not exist, is using mobile test. You can see here in the image is that type of device that's being used. And that's typically employed on penetrations where the efficiencies are naked to the visible eye, and by doing this type of test, you can see bubbles that start to appear, indicating that there is some sort of air leakage. So this type of testing is beneficial for everyone on the construction site. You can also be doing a pressurized test as well at certain locations of buildings, such as your windows or walls, just to make sure that the air tightness levels are being met. So one of the questions we might be asking is, what is the sweet spot in terms of targets? What are we looking for in terms of owners and building designers and so forth? There is no answer for that. Every building is unique. Every building has its own challenges and opportunities, and there are no silver bullets of which retrofit strategy is the best or should be employed. So I'm showing you a graph that I took from a project that I'm working on for a hospital, showing varying degrees of different types of retrofits that we can be doing, from increasing the overall wall R value, the roof R value, window to wall ratio, and even solar heat coefficient. You can see kind of where the line guides up to how much energy is being used. And this is almost a scaling effect. So you might consider, increasing the wall insulation levels to a higher level, but that may decrease the amount of roof insulation you may need, and so forth, window and so forth. So there are no really silver bullets here. It's all about good design and good practice. But literature has provided some insight of what the target should be if you're you're trying to achieve net zero. And I've just showed some here. This, again, it may vary depending on the type of building, but for ceiling and roofs, we're looking for R50 to R60. That's more or less 11 inches of ply iso insulation. That's a very thick roof. For above grade walls, we're looking to R30 to R40. That's 9 inches of semi-rigid insulation, more or less. Windows are 6 or higher, and that's usually achieved through triple glazing. For below grade walls, we're looking for R20, foundation slab, R10 to R20. And for air tightness levels, quite rigorous, we're looking for 1 air change per hour at 50 pascals. So just to recap so far of what we discussed, there are no silver bullets. We're relying on really good design to figure out what is the best way of tackling these buildings. Major enclosure upgrades happen every 20 years, as Christian said. We've already missed that first opportunity a few years ago. We are now reaching that sweet spot of where major interventions are required, and there's an opportunity to upgrade your building. Another point I have here is setting minimum targets. Setting minimum air tightness targets, R-value assembly targets, and so forth, so that there's a clear objective of what should be met for the overall building. And this can be aligned with incentives. There are plenty of incentives that the municipality of Toronto and Vancouver and so forth offer, include federal as well, to help incentivize doing these types of retrofits. And for depending on the type of building, that might be more cookie cutter, prioritizing the portfolio as a whole or a neighborhood together. This is all a iterative process. So there's a lot of thinking that goes involved into this. And we require everyone at the table to come and brainstorm ideas from contractors to architects and owners. It's important that we all come together as a team to figure out what would be the best solution for your type of building. So I want to get to a few case studies. The first one I'm showing you here is the OAA headquarters. It's a complete net zero retrofit. It was at a budget of $8.5 million, and it was completed in 2019. So the OAA headquarters was initially constructed in 1989, and it was constructed to the R2000 standard, which was the high benchmark of its day. So 25 years later, the OAA was facing a lot of maintenance issues. A lot of components were degraded, and they needed a lot of repairs to keep the building up in place. They've also ran out of space as well, so they're looking to either potentially relocate into a new location or fix what they have on site now. So the OAA worked with consultants for over 3 years to research what would be the best solution to reach net zero targets, meaning eliminating the use of fossil fuels and electrifying as much as possible. So they've achieved this through a variety of different ways. I'll get into that, but mostly it was achieved through a geothermal system that was installed, solar panels on the site providing renewable energy, and of course a high performance enclosure. So just giving a brief overview of what that building looks like. I've showed you a floor plan of some of the programming that's in space, a lot of offices, conference rooms, terraces, and so forth. It's 22,000 square feet. The building is 3 stories high. And something that's interesting about this building, it doesn't sit on the grade, it's actually elevated, which means it's a lot of soffit area. So some of the features that were installed at this facility, besides the solar panels and the geothermal, there's a lot of dynamic glazing, installed like conference rooms, kind of shed the light, encroach how much light is coming in. There was upgraded thermal insulation at the soffits and at the walls, and the windows were also replaced. So getting into a little bit of the details here, the existing system had an R10. It was a modest amount of insulation that was in aluminum panels, but one of the first things we did is that we actually replaced the Z-girts that was supporting the system. And these Z-girts can degrade the system up to 50 to 60%. So changing the Z-girts to a high-performing clip, such as fiberglass or stainless steel, has already done a tremendous amount of benefits of improving the overall R value. In addition to that, we also applied spray foam in the walls to kind of help with air in the building and also bump up the R value. And air tightness improvements were made through the use of liquid applied membrane to seal cracks in the wall. and in the concrete and in the soffits to make sure the air barrier continuity was there, the transit, especially at the windows. And in terms of the windows, we've also installed new triple glaze for the majority of the building. These were fiberglass frames, the original were aluminum, so that was a huge win. And the existing curtain wall that was kept in place was retrofitted with fiberglass pressure plates as well. So when it came to the soffit, again, like the soffit was a large area, this building is elevated, so this was one of the key areas we wanted to tackle. So a lot of the mechanical systems were removed as part of the HVAC switching with the geothermal system. So a lot of the penetrations were sealed. We made sure that the area continuity was in place. And we also added a fair amount of insulation as well to bump up the R values. The soffit insulation clips were also changed to a higher performing one to also increase the overall performance of the building. During this process, we also did a lot of air testing throughout construction as quality control. Again, like I mentioned before, a lot of deficiencies can't be seen with the naked eye, especially when it comes to membranes. So we've used air tightness testing at multiple phases of the project. And you can see here at several times in the building, we did come across some levels where heat was escaping. So through this process, we've managed to identify deficiencies early on and address them right away before the cladding was finalized. So getting to more core Toronto, 77 Bloor Street is an interesting example where we worked on, where the retrofit strategy focused more on the HVAC and commissioning. And as a result of switching the systems, the building owner was able to get a new occupiable floor space because the equipment that was in this building previously was no longer required, and through efficiencies, they managed to gain this floor space. You can imagine the incentive for this owner to do these types of retrofits. They managed to get a new floor space, more tenant, which means more revenues to pay off the retrofit. No significant changes to the building envelope, but we did replace the windows. But just want to show this example that building envelope is important, but there are different ways of achieving close to net zero. This building did not achieve net zero. It could have if it decided to fuel switch, but it almost made it. So flip to 60 Bloor, just a few blocks down. So this is a 14-story office tower in the northeast corner of Bay and Bloor. 20,000 square feet of office space and 40,000 square feet of retail. And this was built in 1970. And contrary to 66 Bloor, or 77 Bloor rather, the building envelope has been retrofitted. And you can clearly see here, and there's a variety of reasons for that. The main driver was, again, for performance, but the owners wanted an opportunity to renew the appearance of the building. So they decided to put in high-performance glazing systems, a lot more spandrel areas as well. And in this process, they also retrofitted the HVAC system as well. So just want to highlight here that building envelope, I'm talking a lot about the details of waterproofing and membranes and insulation and so forth. There are benefits from a thermal perspective, but also from a financing and leasing perspective, right? If the building looks good through these retrofits, you can attract a lot more clientele, and you're also making the building thermally perform as well. So just want to end with a few more slides here. A couple of slides just talking about the planning process and how these retrofits happen. So planning for a holistic retrofit, it's all about evaluating the performance, doing an energy audit or recommissioning, doing a condition assessment of the facade just to see what type of system is in place now, what can we do, what are the deficiencies on site we need to tackle. So when we discover these opportunities, we often present a business case, and this is when the costing comes in place. So we look at the impact in terms of energy performance and the impact in terms of budget. And that's where the iterative process starts, of trying to figure out what is the best solution for this building owner depending on the budgets that they have. Just want to end with this slide here. I saw this recently, and it's, COVID. It's a funny depiction of what's happening, and there's a lot of excuses that happen of why these retrofits can happen. First it was COVID-19, we're in the onset of a recession that's happening, but the biggest wave that's going to be coming in the near future is really climate change. So look for opportunities now, try and engage the conversation with the clients, even if they're not willing. Any progress is better than none. because at the end of the day, climate change is coming, whether we like it or not, especially with the recent news of floods in Pakistan and hurricanes across the globe, those are happening more frequently. So addressing our buildings now is going to benefit not only the building owners, but everyone here in the room. So as a summary, I just want to go over some points again. Prioritizing projects, integrating short and long-term needs, so short-term repairs, but hopefully these will include deep energy retrofits. Phased projects if needed. This does not need to happen all at once. Projects can be phased so that these retrofits can be implemented. Understand the client's needs and goals, and then implement the projects using the quality control procedures of what is specified. That's always key, is when you guys come in place to execute the work and make sure it's constructed well. And then, maximize opportunities. Think beyond the facade, think future ready. Think about the incentives that are available, not only from a performance perspective, but also financial as well. Just a little bit of what we do is, at WSP here, we do a lot more than just deep retrofits. We do a lot of facade engineering as well, repair, renewal, restoration, and so forth, and some projects that we have completed recently in our portfolio here. So this concludes the presentation. Thank you so much for joining us today. I'll open the floor for any discussions or any questions that you guys might have. That was a lot of them. Right, guys, there's no further questions. Thank you so much. I hope you guys are enjoying your time here, and look forward to talking to you guys at the tables here. Thanks.
Okay, thank you, Jason and Christian. Yeah, you certainly had a call to action. I think a lot of our members here are very proud of the work that we do in the community at large, and certainly the way you've highlighted some of the energy conservation measures and the work that we do and how it's contributing to the greater good, I'm sure made me feel good about the work that we're doing beyond just dealing with a project for an owner. It's actually more globally, and that's exciting. So I'm also excited for our members. If deep energy retrofit is trending in such a significant way, which obviously it is, it's mandated by code in the future. It's a business opportunity for everyone here as well, right? So that's certainly exciting. Thank you. We do have a small token of our appreciation for Jason and Christian. Here you are. I'll just pass it to you, but thank you for participating today. And just for a SWA update, we do have nominations for the board. There's 2 open positions. Nominations are due October 10th. You are required to send your bio and a photo to Betty. If you are interested in joining the board, it's a pretty large board, so 2 open spots does not mean that you're going to get dumped with all the responsibilities. So don't worry about that. The fall edition of the bulletin we've issued, or we're soon to be issuing another edition of the SWA bulletin. As you may recall, we had a spring one. We are having advertising opportunities, quarter-page advertising opportunities. And we also are featuring members in action, and some of this stuff here would have been great. So Jillian, if you want to put a members in action thing regarding deep energy retrofits and how you're partnering with some of the manufacturers and contractors in the room, that would be awesome, or whoever at WSP. But anybody in the room can feature a project of theirs, and it will go out on social media and in our bulletin. The new website, we do have a new website, the Sealant and Waterproofing Association of Canada. It is different, so please delete the old URL. It's no longer in operation. It does exist. The web developer, I guess that's what his title would be, has gone AWOL. We can't remove it. We don't know how to remove it. So it does exist. And so the old photos, maybe in 20 years, we can still see old photos of ourselves. Wow, how good looking we were. Anyway, upcoming events. November 3rd is the AGM. As you may recall, we're doing it at the Ravine Winery. It's a one-stop location. We meet at the hotel. The bus takes us to the event, and we spend our time there from 4 till 11:30. But there's live music. There's a tasting session, a beautiful dinner, and lots of mingling with everyone in the room and many more people that will be there. So that's November 3rd. The ski day is January 27th at Old Sloy Bluff again, and then we'll have another technical seminar just like this. If you have a subject that you're interested in hearing about, the board is always curious and looking for new technical content to provide our members. I think that's it. Betty, anything else? Did I miss anything? Nope. Okay. Well, thanks everyone, and thank you, gentlemen, for putting on a great presentation. We're very grateful. Okay. Thank you.
Question.